Well, greetings, everyone. Thank you for tuning in to our ASBI monthly webinar. We'll go ahead and get started. Hopefully everybody is here today for the September webinar. I know it's September, but hopefully you're here to see Mr. Corey Rogers with RSNH talk about inspection and maintenance of segmental bridges. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. You see my contact information on screen. I'd encourage you to follow me as well as the American Segmental Bridge Institute on LinkedIn. Unfortunately, you can't just Google search, or I'm sorry, LinkedIn search ASBI, ASBI. You have to actually type in American Segmental Bridge Institute, but after that, we're pretty easy to find. Again, September webinar, and I'll do some quick announcements just to kind of bring you up to speed on some of the things going on at ASBI. Today is our last webinar for 2022. We have our convention next month, so we're not hosting a webinar next month, and then with the holidays coming in, there's a lot of folks aren't really available to do webinars. So we will resume webinars next year in February. It's actually February 22nd will be the first webinar. And just put it on your calendar or in your mind. Our webinars each month are on the last Wednesday of the month from noon to 1 Central Time. So you could just go ahead and put a little mark on your calendar and block out those times if you want to attend our monthly webinars. We'll open up registration for our webinar. Our February webinar will start. The registration will be open then in January. So to that end, videos of our past webinars are available on our website at the same location where you probably registered for this webinar. It's under the Events tab, Monthly Webinars. And you see here on screen a list of all the topics we've covered this year. If you've missed something or you want to go back and revisit, or you have a colleague who missed one of them and you'd like for them to see it, those recordings are available. Unfortunately, we cannot issue certificates of attendance for viewing videos. We're not allowed to do that through RCEP, who is our provider. But certainly we do provide those certificates for folks who attend the webinars live. Another upcoming event is the ASBI convention. I mentioned it earlier. It's October 31st through November 2nd at the Hyatt Regency in Austin, Texas. That registration is open on our website, and I encourage you to register as soon as you can. The hotel is already filling up, so the sooner you get registered and grab your hotel room, the better. So some quick instructions for today's webinar. If you lose connection, you can rejoin the webinar at any time, but of course you'll miss content while you're away. It's sort of like walking out of the room when you're in a conference. I mentioned earlier, we will be issuing certificates of attendance for those who are attending the session today. And I do ask you to allow a week for us to put those certificates together and email them to you. We do a manual process to verify time and attendance of the session. And then we'll do Q&A at the end of the presentation today, and I'll show you how that's going to work. So on your GoToWebinar dialog, you should have a little questions click on the right-hand panel, and you can hit that little questions click and then type in your question. As an attendee, you're muted through the entire session, but you do have the ability to type in questions, and I'd encourage you to do those questions as the presentation goes. Don't wait till the very end. As things come to you, you can just go ahead and type in the questions. We'll hold those all for the end, and then our Q&A moderator today, Mr. Wade Bonzen, will step in and kind of quiz Corey at the end of the session. If you're on a mobile device, you can still type in questions. You should have a little question mark in the upper right-hand corner available to you. Same game, you just hit that little button and then type in your question, and we'll field those at the end of the session. The American Segmental Bridge Institute does meet the required standards of the Engineering Registered Continuing Education Program, and again, all attendees will receive certificates of attendance in compliance with RCEP requirements. So with that, I'm going to turn over to introduce today's speaker and then turn over the screen to our speaker is Mr. Corey Rogers with RSNH. He is a registered professional engineer and has 20 years of bridge inspection, maintenance, and construction experience. Prior to joining RS&H, Corey worked for the Michigan DOT as the engineer of bridge field services. And in this role, he managed statewide inspection, maintenance, and construction of bridges. Corey started his career in bridges, conducting emergency and high load hit inspections. He became the statewide bridge maintenance engineer and developed many of the bridge preservation practices still implemented today at Michigan DOT. Corey then transitioned to bridge construction engineer and managed complex segmental bridge rehabs of bundled projects, a number of I think it was 35 bridges that were bundled together. He did 3 lateral slides and also developed specifications to prevent unbalanced bidding of bridge rehab items. So you can see Corey's experience is broad. It's not just, I'll say, in the field, in the construction, but also on the contract side. He developed, while still at Michigan DOT, he developed the request for action process to prioritize bridge repairs, chaired the MDOT Bridge Committee, and reviewed all bridge scoping reports to ensure bridge assets and funds were utilized effectively. Since joining RS&H in Texas, Corey has served as project manager on multiple construction projects, as well as the project manager for TxDOT's routine bridge inspection program. So with that, I will step over and share the screen with Corey and let him make his presentation.
It's working on it, Greg.
Yep, we got it. We can see your screen and hear you as well.
All right, cool. Thanks, Greg, and thank you to the ASBI Executive Committee for giving me the opportunity to talk a little bit about MBIS inspection and maintenance of segmental bridges. So hopefully y'all learn a little bit about some best practices for both of these topics. We all got a love for segmental bridges. That's why we're here. So let's hopefully you pick something up here. So to start things off, and one of the good reference documents is obviously the FHWA Bridge Inspectors Reference Manual. Even if you've been doing bridge inspections for a long time, it's worth a reread. I feel like every time I dive into that, to the BIRM or BIRM as they like to call it, I learn something new or pick up on something different that can be implemented in the field or our inspection processes. You know, one of the key statements here when we're evaluating a structure is, you know, we're rating the thing on a 9 to 0 scale, 9 being the best, 0 being the worst, on the general condition of the entire component being rated. So, you know, we're making that engineering judgment, that inspector judgment in the field and saying, okay, is this an isolated defect that's not impacting the primary element, or is this kind of systemic across that entire primary component, and do we need to rate it as such? The caveat being, if the isolated defect does impact the structural capacity of that component, then we can use that isolated defect to lower the condition rating. An example of that would be, you know, a segmental bridge. These things can be 1 mile or 2 miles long, so they're quite large. So taking all that into consideration for the superstructure can be challenging, sometimes a lot different than doing like an 80-foot PCI beam, right? So a minor fall, you may not ding it. You know, that's something we can document on the report, but it's not going to affect the condition rating. Where if it's a deteriorated tendon, that's actually a structural element, and it's in an isolated spot, that's going to impact the structural capacity, and that needs to be reflected in the condition stating. So the 2 primary elements I'm going to talk about today are the deck and the superstructure. So you can see here on a segmental bridge, it's basically a concrete box with steel reinforcement tendons. And the top flange also functions at the deck. So there's some overlap there between your items number 58 and items number 59 in your superstructure. And the ratings should match up and be consistent as far as the comments go. And again, here's the code description and the rating scale, 9 being excellent condition, which we very seldom use in the field. I'm not sure if I've ever seen a 9. Typically, we can find something wrong, and you can see here an 8 is also very good condition with no problems noted. And then 7 is a good condition. So anything 9, 8, 7 is considered what we call good. 6 and 5 falls within the fair category, and then 4, 3, 2, 1 is what we would consider poor. So understanding of what's good, what's fair, and what's poor helps you out in the field. And then the whole process is based on a +or-1 scale, where another inspector may come out, they may disagree and be 1 rating off, but as long as we're within 1, then we're good to go, and that's how the system is created. In addition to the overall condition ratings, FHWA and AASHTO have implemented the National Bridge Elements, or NBEs, and these get a little bit further into the weeds, where we're actually identifying specific defects and quantifying them for the bridge owner's benefit, so they can schedule maintenance and address issues before they become so large that they impact the overall condition rating of the component. Take it a step further from the NBEs are what we call the MBEs, the bridge management elements, and these are, again, they're associated with the primary element, but they're on top. They're a protection system for the primary element. So think like bridge painting. The paint protects your steel, which is the steel beams are the primary element, or concrete surface coating, expansion joints, protect everything underneath it. So it's another layer of documentation that bridge owners can use to better manage that structure. And I'll give you kind of here's some the common MBE numbers that you're going to see, and these are pretty consistent. So for a segmental bridge, you're going to have MBE number 15 for your deck and slab, 104 for your superstructure, then a couple of the bridge management element numbers you would typically see as 520 deck slab protection system, which could be a thin epoxy overlay or a silica fume or latex wearing surface, and then 521 as an example, concrete protective coating. So you would rate that as what you see in the field, and then it gives the owner the information that they need to schedule the maintenance that's applicable to that particular item. So an example of that, if you're out there without the elements, or a combination of the MBI condition rating and the elements, it makes it more challenging for the owner to maintain that structure. So say, for example, you have 5,000 foot long segmental bridge, and you do have that spall location, and it's a minor spall, 4 square feet. It's not a big deal. It's not going to impact your overall condition rating, right? You're going to keep it at a 7. You're going to say, this isn't systemic. This is an isolated issue. I got 5,000 feet of concrete that's in really good shape. I'm not going to drop my condition rating from a 7 to a 6 or 5 because of this one spall. However, if you maintain that that condition rating until that spall gets to the point where it's impacting structural capacity, say it gets deeper and deeper, and you start seeing rust leaching from it, and you're getting tendon corrosion as a segmental, now you're dropping it to a 6 or 5, and you're not capturing that defect until it gets to that point. With the element system, you're able to quantify that spall at an early phase and allow the bridge owner to get out there and do some patching, some rehab of that particular defect before it starts impacting your condition rating. So they really work in unison, and in particular, we really like the use of elements on these really long structures where you're typically not going to have systemic defects across the entirety of it, if that makes sense. So pre-stressed concrete box girders are designed to limit tensile stresses in concrete. Therefore, cracks need to be identified and thoroughly investigated to determine causes and severity. So, think of it as it's a typical reinforced concrete structure. One of the primary objectives of the concrete is to protect the steel and keep it from corroding. I mean, the steel is carrying all of your tensile stresses. So whenever you have a crack, that opens it up to water infiltration, chlorides, which can facilitate corrosion of your steel, and that causes bigger problems. So cracking is always an issue. And concrete cracks. I mean, it's going to crack, and we're just going to have to document it, watch it, determine what type of crack it is, and then what's the best method of mitigating that cracking or sealing it up and preventing that infusion. Best thing is visual and physical inspections. You got to bang on concrete to get a feel for it. Sounding rods, hammers, chain jags are pretty typical to find D-lams. Once you're out there in the field banging on stuff, you can really feel you can feel the D-lam, and you can also hear the sound of the sounding rod. It makes a dull thud if there's a D-lam, where it's more of a high-pitched ping through the bar if the concrete is sound. We have seen where folks use crack gauges with different color keel to document it through every inspection to show cracks, like, okay, this is a crack from 2012 to when you're out there in 2014, use a different color and document it. That way you can kind of document the stage and progression of any cracking that you see, even if it's minor cracking. And then I just want to give you an example of what can happen here. So this is an example from Texas on a precast box culvert, and this is what I like to show folks, the difference between a visual inspection and actually banging on things. So this is a crack, and from a visual standpoint, in the top slab of the culvert, if I'm looking down the culvert and I'm looking at this thing, I'm like, okay, we got a crack there, no big deal, right? Concrete cracks. It's worse than your minor 1/8 or 1/16 inch crack, where I'm going to rate this a 6, knock it down to fair. Well, if you get inside this thing and bang on it, that concrete is actually really bad and falls off. And you can see here, you're probably pretty close to 50% section loss on your transverse top mat steel for this box culvert. This ended up requiring a load rating and posting, which resulted in a condition rating of a 3 of a critical finding. So this just kind of demonstrates how important it is to bang around those cracks and determine the validity of the concrete. What condition is that concrete in? How stable is it? Is there anything going on underneath there that's causing that crack associated with the steel? So some other common deficiencies occur and to watch out for in segmental bridges. Cracking, I talked about that, and I'll get into the different types of cracking and kind of how to identify those. Some of these other highlighted ones, efflorescence, that's a result of moisture and chloride penetration affecting your concrete. Usually you're going to see some rust leaching associated with that, or in conjunction with efflorescence. Alkali silica reactivity, ASR, a lot of times you have cracking or delamming, you really can't explain it. It typically has something to do with the aggregate or something with the concrete mix as alkali silica reactivity. In those instances, you can take a core. A lot of departments and bridge owners, can tap into some geo experts that can do an analysis and determine if it's actually an ASR issue. Collision damage, again, these are long structures. If you, 1.5 mile, 2 mile long structures, they're just more susceptible to cars running into barrier walls and banging the things up. Internal steel corrosion, again, whenever you see rust leaching on a segmental bridge, it raises a red flag. You need to do a deeper dive into that. And then loss of pre-stressing, you'll see some cracking around your anchorage terminals or some tensile flexural cracking as a result of those loss of pre-stress forces. So again, this is out of the berm. I just kind of consolidated the different cracking schemes here. So, shear cracking is going to be diagonal around your bearing areas. Tensile is going to be in your positive moment sections on the bottom of the slab, similar with the flexural. Anchorage, your segmental bridges inside will have these bump outs here where the tendons are locked off and anchored. If you don't have the required reinforcement here to support this anchorage, you could see some cracking around the anchorage. Web splitting, this is fairly unique. You might see some spider cracking here around continuity tendons. Torsional, again, it's especially structures on a curve. You may see some torsional cracking, and it may not be continuous. You may see what seems like a shear crack, but then you have some bottom slab cracking that's abnormal or not in a tensile zone or maximum moment zone, And once you sketch this out, as you get your field measurements, then you can kind of make more sense of it and say, you know what, that might be some torsional cracking going on, and do a better look at it, pull some more resources in to take a look. And then thermal cracking, this is pretty typical. Your standard shrinkage cracking, we don't get too excited about it, but we do want to try to keep those cracks as tight as possible to prevent moisture intrusion. You know, I talked, the deck and the top slab are basically the same element on segmental bridges, and the top flange will be covered typically with a wearing surface, just to give you rideability, to give drainage. It protects your steel in your top flange and your transverse post tensioning for your wings that are carrying traffic. And those could be latex modified overlays, silicone fume overlays. Now we're seeing more polyester overlays across the country. Epoxy overlays are still popular, or some other type of high performance concrete. Bridge joints are a critical part of the structure. They allow it to move. Segmental bridges move quite a bit, so you're going to see what we call modular joint systems. Your typical joint system gives you about 4 inches of movement on a standard concrete steel bridge. Because of the spacing between joints on segmentals and the amount of movement that you get on these things, you're going to see a modular joint that is consistent of multiple strip seal glands. You see this is an example of 3. So each of these gives you about 4 inches of movement. So you're looking at 12 inches of movement total. And that's why you have these big steel plates here on the barrier wall, because this can open up to the point where a pedestrian or somebody could fall through it. So it's important to keep these protected. So not only do they allow the bridge to move, it provides wheel load transfer across them. It's a watertight seal, so that water doesn't impact any of our critical components below. When you're inside the box, one of my recommendations is to get in there and stand underneath these things while traffic's going over it. And typically you can hear an issue with these joints. They should be pretty quiet, other than the wheels, you know, going across them. But if you hear any kind of slapping or clicking or metal on metal sounds, it's probably an indication that you're losing your neoprene bushings, or you have a cracked weld somewhere on these things, and it's going to need some type of remediation or replacement. The barrier and fascia opening should match your joint opening as well. Otherwise, it's going to be a pinch point. We've seen a lot of instances where the joint accommodates 12 inches of movement, but the barrier wall is only cut for like 4. So, you know, during hot weather, when this thing's really expanding, the barrier wall is going to pinch up before the bridge does. You're going to get crushing of the barrier or the fascias, or it's going to impact the bridge in some other capacity and cause some cracking that you really don't want. And then also make sure these things are set and slightly lower than the wearing surface itself, especially in northern climates where you got snowplow damage. Plows catch these things, and the plows will win and the joints will lose. And they'll bend them up, crack the concrete around it, and then they'll start leaking, and it's kind of a downward spiral from there. Bearings, another critical component of segmental bridge. Again, talk about the movements. These things have to be able to move. 2 of the bearings you're typically going to see on a segmental, just because of the weight of these things, is the old school was the pot bearing, and the new school is the disc bearing. On the Zwacky Bridge project in Michigan, we actually replaced a bunch of these pot bearings and replaced them with the disc bearings. They serve the same purpose, just one's in, you know, newer style, fewer components, easier to inspect and maintain. And you can see here the pot bearing, they're multi-directional rotational, but you have this elastomeric pad, you have an internal sealing ring, a steel piston, PTFE, and a stainless steel top plate. So the failure we saw in Zwacky was they were over rotated. Right from the get-go, we were having issues with the internal sealing ring, and we were actually losing some of this elastomeric pad. And this neoprene was oozing out of it. It was under so much pressure, it was actually becoming a liquid and oozing out of the ring. And then we were getting some gouging on the steel plates that was causing the structure to bind up. So we swapped them out with these disc bearings, and you can see there's fewer components. Primary component is this urethane disc here. You have the stainless steel and the PTFE for your bond breaker and your sliding. And then you just have this threaded pin through the center, which you really can't see. But so as an inspector, you're just looking at this neoprene, looking for any bulging, looking for any gouging in your steel plate, and then just documenting the movement and the rotation of these things if anything seems out of whack, if one of your corners is tighter or something abnormal going on there. Drones, I mean, drones are becoming more and more popular. We really haven't found, we haven't fired all the bridge inspectors and replaced them all with drones yet. It's still hard to beat the, hands-on inspection and the visual inspection of actual bridge inspectors, but they do come and use them. I mean, they're getting better and better with these LiDAR scans where they're giving us a good 3D visual. We like to use them as kind of a preliminary analysis for pier caps, especially if traffic control is tight. Sometimes you're getting a snooper out there in lane closures. You're restricted on what you can do and what you can close and your time constraints. If you can fly a drone up a 100-foot pier and get a look at it, look at the video and identify any cracks or target areas where you need to then get a hands-on inspection, that's a good use for them, almost like a reconnaissance operation. And then you can follow up with the hands-on and better manage your time. Non-destructive evaluation, if we find that rust leaching or there's concerns or cracking, loss of pre-stress, or we think something's going on with the tendon, we do have the technology now to do a deeper dive into that and actually look at these tendons while they're in place. I like to reference BDI. They got a lot of this technology for use. So I stole a bunch of their stuff, but they're doing tendon bore scopes. You can do this ultrasonic tomography, this MIRA scans that actually give you an idea of where some grout voids may be or what the condition of your tendons are. And then you can actually do a small core hole, get a bore scope in there, and actually get a visual on your steel and see what kind of condition it's in. So that technology does exist to look at these things in further depth. So for the maintenance, think of it as it's a typical reinforced concrete structure. It's just big. It's concrete and steel. We want to keep the cracks tight. We want to keep the cracks sealed and protect all of the steel that's internal to the concrete. Cleanliness is key. Some of the, I'd say a lot of the success for Zilwaukee Bridge is built in the late 70s, early 80s. Still looks great. Is the maintenance guys have always done a good job of keeping the birds out. Like I said, you got 12 inches of movement at these expansion joints. The maintenance guys on Zilwaukee, they had a system that the fencing for the bird fencing, we call it, actually slid, expanded and contracted with the bridge to keep those out, so it wasn't a constant maintenance headache. But birds or other critters get in there, they can make a mess of it pretty quick. Bird droppings hold moisture, which is bad. It starts deteriorating your concrete, your steel. Keeping debris and litter picked up off the top along the barrier wall. Make sure your drains are clean and water's flowing properly. Normal sweeping of your bridge deck. Vegetation control, not only for inspection purposes, but again, you don't want that moisture up against the piers. Make sure your joints are cleaned out and functioning properly. Graffiti control, and then have like an accident response situation. Again, vehicles get stuck up there, it can become a bigger problem. Make sure you got access for aerial equipment. Keep everything, if you have a maintenance road down below, keep that maintained so you can get down there quickly. Having brush control and grass mowing is nice because you have quick, easy access for bucket trucks or aerial equipment if you need to. Crack injection is a big one. Concrete patching, carbon fiber wrapping is a new thing we're seeing. West Seattle Bridge just did a ton of carbon fiber wrapping to strengthen it. External post tensioning is kind of above and beyond. That's the next step. If you have an old bridge that needs some additional strengthening, and then controlling that scour and erosion, and then structural health monitoring. We'll talk a little bit about that. So crack injection is the biggie. You know, seals these cracks up, keep the moisture from getting inside. You can see this guy here, he's doing the crack injection. There's these, first step is to place these ports along the crack. And we typically space these the distance of what the web depth is. So if you have like a 2-foot web wall, you want to space these ports 2 feet because the epoxy will move in a 360-degree circle. So as you pump into this first port, once the epoxy starts oozing out of the second port, you know you got full depth penetration of that epoxy through the entire web of that slab. And then you kind of work your way across. You cap this one, move your pump to here, so it starts oozing out of this one, and then cap, and then just keep working along the crack that way. I mean, it doesn't look pretty, but you know, you can grind these down and do a concrete surface coating over it, and then you won't even know it's there. Nice thing about these epoxies, you know, some people are like, well, I can't monitor the crack if I do an epoxy injection. Most of these systems, stuff is just as brittle as concrete. So if your crack is propagating, these epoxies are going to crack, and you can still determine if the crack is moving or working while trying to seal it. Carbon fiber wrapping, it improves shear and flexural strength if you need it to. It's also for confinement for concrete patching. I know sometimes it's difficult to do an overhead patch and have it stay in place. So doing, you know, covering that with some carbon fiber can help hold that concrete in place. It is surface prep dependent. You got to have a clean surface like a lot of other things. And carbon fiber, it is susceptible to impact and UV damage. You know, hit it with a hammer, it's going to break. And it doesn't like the sunlight, so you want to have like a polyurethane surface sealer over top of it to protect it against UV once it's complete. Surface prep, again, with concrete remediation and maintenance, concrete surface preparation is critical. You need it for your overlays, wearing surface overlays, thin epoxy overlays, crack injection, carbon fiber wrapping, concrete surface coating is all dependent on the prep. You'll see in specifications a lot of times they call out a CSP, a concrete surface profile, and this could be a number. You see over here CSP 1, 2, 3, all the way through 9, and kind of what it alludes to. But again, I mean, if you're not familiar with what a CSP 3 is, it's kind of hard to tell the contractor when to stop doing the prep or if they need more prep. The International Concrete Repair Institute does sell these CSP chips, and these are really valuable for in the field because you can actually hold it up against concrete and say, yep, it matches my profile on my chip, you're good to go. So I highly recommend if you're a construction inspector and you have a project to carry a set of these chips in your truck with you. Thin epoxy overlays, again, multiple ways to put these on. I've seen crews that do it with the bucket system. I've seen trucks, automated trucks that are mixing this thing and spreading it all in one shot. It really doesn't matter as long as it's getting the job done. Thin epoxy overlays will bridge the crack and sit on top and have a heavier aggregate. Typically, they're 2-core systems. A penetrating healer sealer will penetrate the crack, and then it just has a sand aggregate on top just to take the sheen off. So they're a little bit different. Crack chasing is basically using a ketchup bottle, mixing the stuff up, and then if your crack is fairly spaced out, you can just kind of walk across the bridge deck and seal them up with the maintenance crews. Deck patching, you want to do all the deck patching prior to putting the overlays down. If you're concerned with skid resistance, the bauxite aggregate is hands down the best aggregate you can use for long-term skid resistance. There's been numerous tests on this against other aggregates on the industry, and bauxite, it just outperforms all of them by a long shot. And one thing to consider, you know, before going full blown with thin epoxy overlay is you know, what does it do to the dead load on the bridge? You know, some of the older segmentals, they're right there on the cusp of, you know, rating factors of a 1.0 or just above a 1.0. And you do add quite a bit of weight if you go with the 2-coat thin epoxy overlay with the amount of aggregate that you add, and it may be enough to push you over where your rating factor drops below a 1. So it's something to check before you jump into a thin epoxy overlay. Internal post tensioning, you know, this is where you do have those issues with inadequate tendon reinforcement in your bridge, the structural capacity. US 31 over Muskegon was just that. We had a lot of shear cracking and that anchorage cracking that we talked about because we didn't have enough reinforcement around the anchorages or in the shear zones. So we did an external tensioning project with deviator diaphragms and then double harp tendons. And you can see how the tendons harped up through the pier diaphragms and then back down, and then we stress these things and basically squeeze the bridge back together, close the cracks up. Some lessons learned from that project, ground penetrating radar is can be very accurate or it can be really sloppy. It depends on the firm. Luckily we had just gotten off a previous segmental bridge project where we had really good ground penetrating radar contractor that was, right on the money with their locates of their tendons and critical reinforcing steel. So when we got to Muskegon, the first GPR contractor was out there and they whipped through it. Took about a day for them to mark everything off, and they were off plus or minus 1.5 inches, 2 inches, which is too far for us because we were splitting hairs, corn through bars, that with 3-inch spacing. So plus or minus 2 wasn't going to cut it. So we had another contractor come in and then they dialed it in and got us right on the money. But if we wouldn't have known from our previous project that what the capabilities of GPR, we would have bought the old saying, well, that's as good as we can get. We can only get within 1 inch or 2, which isn't the case. You can get it perfect if you get the right crews out there. As-builts. On the Muskegon project, the as-builts were great. They were right on the money. I mean, we were able to pull tape, use the as-builts, pull tape measure, and 9 times out of 10, we were right on top of the tendon we were looking at. So we would do some pilot coring just to make sure it was there, but luckily, having a nice, good set of as-builts goes a long way. So if you're on a construction project building a new segmental, remember the guy 20, 30 years from now doing maintenance is going to love you if you take the time to put together a good set of as-builts. Make sure you're using the proper specs and equipment. We learned the hard way that this rebar here for hammer drills bits can cut rebar. So we ended up kicking those off the job. We were under the impression initially that we can use a hammer drill, it won't cut steel. So if we hit steel, we're in good shape. Well, these things did cut steel and we had to make an adjustment to our coring plan. And experienced operators, the guys that are doing the coring or the hammer drilling, they can feel it. They can tell when they're on bar or on steel. Slurry will change a different color. It'll sound different. It'll feel different. So having experienced operators out there goes a long ways when you're doing some of this this destructive coring for PT rods or reinforcement. Erosion control, maintaining the channel is critical for your foundations. These segmental bridges got large foundations. A lot of times they're pile supported or drilled shaft supported, but you still want to protect them from scour. Animals get in there, varmint control. Make sure you're inspecting the riprap channel. If there's gabion baskets, documenting those. You're seeing now the use of articulating concrete block. Those systems are really dependent on everything being in place the way that it's supposed to be. So if there's blocks missing, a lot of times kids are out there fishing, like to screw around and grab these blocks for rod holders or whatnot. And, just make sure everything's intact and you're documenting that and the foundations are protected the best that they can. And then structural health monitoring. This is a capability. If there's any concerns with heavy loads or cracking, the technology is there to place strain gauges in a laptop and wireless or modems and power them to send 24/7 real-time data to any bridge owner's office and monitor it. We did this. This was a setup we had on Zwaukey Bridge where we're actively monitoring strain gauges at some cracking locations so we could keep an eye on it. It was pretty slick because we had one instance where there was a traffic jam on the bridge and there was actually a PCI beam was parked right over top of this location. So we knew about the time and day that truck was parked over that, so we could go back through the data and find that time frame and go ahead and evaluate it. And it showed that we weren't even getting any strain gauge data from from having a really heavy load parked right over top of it, which made us feel pretty good. So that's the quick and dirty of it. If anybody has any questions about inspection or maintenance, I'm happy to help.
Yeah, thanks,
All right.
Corey. Sorry, go ahead, Greg.
Yes, so I will go ahead and introduce our Q&A moderator here real quick. Let me switch over. So our Q&A moderator today, and actually will be joining us even next year, is Mr. Wade Bonzen. Wade is the chair of ASBI's Construction Practices Committee. And my screen just went blank. That's interesting. There we go. So Wade is Vice President and Director of Operations for FIG Bridge Inspection based in Dallas. He earned his Bachelor of Science degree in Civil Engineering from New Mexico State University. Also holds a master's degree from the University of Texas at Austin. He has more than 25 years of experience in design and project management of major segmental bridges. He's also a registered professional engineer in 10 states. And so with that, I will turn over the program to Wade to do a little Q&A. Those of you all who are listening in, you're welcome to continue to type in questions as Wade goes through Q&A, and we'll just kind of have a little open discussion here with Corey. With we have about 15 minutes left in the session today, so there's plenty of time for questions. So with that, the floor is yours, Wade and Corey.
All right, thank you, Greg and Corey. Great presentation, very informative. We do have a few questions that I'd like to from the audience that I'd like to pose to you, and I've got a couple of my own if we have time, but we'll start with audience questions first.
Okay.
The first question goes back to the overall structure rating scoring, and you mentioned that getting a score of 9 is essentially unheard of in the bridge inspection industry. And the question is, would it not be a 9 basically immediately after construction, like perhaps during a baseline inspection?
Yeah, I think that boils down to kind of bridge inspectors being OCD when they're doing their ratings. I mean, we can always find something that's wrong from construction, whether it's a hairline crack or some honeycombing or some bug holes in some beams. I think it's one of those cases where if they didn't have the 9, everybody would be afraid to use the 8. So typically, right after construction, immediately after construction, most inspectors are going to rate those elements at an 8, unless they see something that really went wrong during construction. You may bump it down to a 7. I think the 9 is there so that folks are comfortable using the 8. I mean, we just never see it. But and then after one cycle, after a 2-year cycle, that bridge is typically going to fall out of that 8 into a 7, which is still good. And then it could live in that 7 for 20 years, until you start really seeing something problem that's going to knock it down into a fair. So as long as you're in that 7 or 8, and you're quote unquote good condition, most bridge owners are happy with that. If that answers your question. I mean, you could. I'm not saying you can't use a 9. I'm just, usually you can find something to ding it to an 8.
All right, very good. Yeah, and the next question is sort of similar to that, but at the other end of the scale. Regarding the 0 to 9 scale of structure condition, what scale number or conditional group initiates the owner to consider the structure to be unsafe and maybe even closed or load posted?
So that would be a 3. 3 is what triggers what we call a critical finding. And a critical finding is typically associated with part of the structure being closed. Whether it's say a pothole in the bridge deck and you're closing a lane or a shoulder, or part of a railing is so bad that you have to close a shoulder. Anytime you do any sort of closure on that bridge that impacts traffic, there's a critical finding that's associated with it, and that element is going to be rated a 3. So that's when everybody starts getting excited. You're very rarely on the opposite side ever going to see a 2 or a 1, and that's kind of why the bridge inspection program exists, right? So you can track that as it falls from a 7 to a 6 to a 5, and then you start getting into a 4, and when you're in that 5-4 range is when that bridge should be programmed for some major rehab to address it before it falls into that critical condition. But every so often, you know, a bridge will, you may be, you know, steel pile bends is a big one where they've been covered with water and you can't get a visual on it. Well, then the water recedes and all of a sudden you have a ton of section loss and you realize, oh wow, this is a big deal. You're going to rate those steel bends a 3, and you may close the bridge down until you can get a structural analysis or some steel repairs done on that. So I guess to answer your question, 3 is where we start load posting, shutting stuff down, and getting really excited about it.
Well, and then Corey, this is Greg, I will add from my experience at TxDOT, you know, procedurally, you won't look in a database and see a number and go, oh, well, we need to go close that bridge. It works the other way around. The bridge has already been closed before it ever shows up in a database as being unsafe or needing to be closed. That's
Right.
one of the reasons we put eyes and boot, you know, eyes on the bridge and boots on the ground, you know, who can make those judgment calls in the field to call for a closure if one's absolutely necessary.
Right,
And
and if you're and when you get into a 5 or a 4 situation, we have the ability to bump up the inspection cycle, right? So I mean,
That's a good point.
we're required by law to look at everything every 2 years. If we're in a 4 and we're like, all right, you know, this is starting to get bad, we can recommend 6-month inspection cycles, 12-month inspection cycles. You know, say, hey, I don't think we need to do anything yet, but let's look at this thing in another 6 months, and we have the ability to crank that up if we have to.
Yeah, that's a good point, and I think that's an important point for everybody to remember, that, you know, these numbers don't exist in a vacuum. They're a communication tool, but really, they're, you know, the biggest issue is getting somebody out there to look at it and then reacting to whatever is actually seen. So that's a great point. All right, here's another question, and I actually had the same question here. Is there a way to discern or identify cracks that are the result of ASR versus perhaps cracking that may not be related to ASR?
Yeah, I mean, for like a PCI beam is a good example of ASR. You know, you're going to see that crack along that bottom flange, like along your steel, that's not really associated with any rust leaching or anything, and it's pretty bad. It's pretty, I mean, you'll see some separation. It's not going to be like your hairline shrinkage crack. It could be 1/8 of an inch to 1/4 of an inch thick. It's almost like a solid D-lam that's fairly systemic. That's what's going to tell me and say, okay, there's something going on with this concrete mix or the aggregate, and this isn't a result of an isolated area where I got a little bit of rust, pack rust, that's popping that concrete off. So again, I mean, if you got the shear cracking, diagonal cracking, you're like, oh yeah, that's shear cracking. You got some hairline cracking, kind of sporadic about it. You're like, all right, that's probably some shrinkage cracking. If I got a significant crack along the bottom of that slab that looks like the whole bottom of the bottom of the box is about to peel off, that's probably ASR. It's pretty nasty stuff when you see it, and it's gonna raise some eyebrows, and you're gonna want to do some digging when you see the cracking associated with ASR. I got a good picture of some ASR and some PCIs. I should have threw it in there, but maybe for the next one.
Okay, interesting. So it's not necessarily, it's a variety of factors that go into it to try to determine whether ASR is a possibility.
Yeah, I mean, most of your delaminations are associated, you know, you got water that gets in there, your steel starts corroding and expanding, and then your concrete, you know, it's not strong and tensile, so it pops off, right? ASR is the same concept, except it's associated with the alkali silica reaction between your aggregate and the cement. So it's actually like an internal chemical reaction that's doing the same thing that the steel rusting is doing, except it's throughout the entire concrete mix.
Okay. All right, here's another interesting question. I'm not sure what this refers to, but hopefully, Corey, you can shed some more light on this. The question is, have you used any of Federal Highway's long-term bridge performance programs protocols for bridge inspection so that the data is gathered in the same way for research and comparison purposes?
I'm not sure what they're asking there as far as the long term. Can you repeat that again, Wade?
Yeah, have you used any of FHWA's long-term bridge performance programs protocols for bridge inspection so that the data is gathered in the same way for research and comparison?
Yeah, I mean, I guess I don't know how, and there is some long-term, there's a federal process where you can extend the inspection cycle out to 4 years, and it's typically associated with newer concrete bridges. I don't know if that's what they're asking, or if it's more of the data collection thing. But I mean, we're pretty standard on how we're collecting data across the systems. So again, maybe I don't, if they want to reach out to me separately and clarify that, I can get back with them, Wade.
Okay, very good. Here's a question about the Muskegon project. It was done a number of years ago. Has there been a follow-up on the repairs to the shear cracks that were done there? And how is the bridge performing since those repairs have been done?
Yeah, it's performing great. I mean, we finished up Muskegon in, what was that, 2013, 2014. So it's had 4 inspection cycles since, and yeah, there's no signs of cracking. Concrete surface coating looks great. You would never know that the crack injection was done from the outside. So yeah, I mean, the biggest thing is keeping people out of it and jumping on those external tendons, because teenagers and stuff like to try to break into this thing and party in there. But that was one of the concerns of ours, was trying to come up with a way to get a grading in there where we could get access for maintenance guys, but keep all the riffraff out of the inside. But yeah, it's performing great. External tendons are looking good. Cracking's been addressed, and it's been in good shape.
So vermin guards aren't just
I know
to
West
keep,
Seattle just did something.
So
What's that?
just to provide a little background, Corey, kind of what's the quick snapshot for everybody who's maybe not familiar with the Muskegon project?
So Muskegon, it was a cast-in-place segmental bridge. It was US 131 over the Muskegon River. It's 3 spans, so there's 2 piers either side of the river. There kept the pier out of the piers out of the channel. It was on actually built on spread footings back in the day, so it's scour critical. And we did some articulating concrete block around the foundations to stabilize the channel banks. And it was originally designed for hammerhead piers, but during the construction, the contractor, of course, value engineered rectangle piers, which affected how the load was distributed from the superstructure down to the foundation. And then just had inadequate reinforcement in the shear zones and around the tendon anchorages. So we watched it for years, and the thing was cracking and getting worse and worse and worse. And finally, it got to the point where Michigan was like, okay, we got to do something about this bridge. Got a rehab project scheduled and a designer on board to do the external reinforcement and strengthening. We call it external. It's inside of the bridge. You can't see it from outside or driving over it, but it's not buried in the concrete like normal continuity tendons are. So we did a double harp configuration. We had to pour, new anchor blocks inside, post tension those. Same with the deviator diaphragms, post tension those. Cored about 400 holes into the thing for the PT rods and the new reinforcement. And then stressed, I believe we had 12 tendons that we stressed. And just to give you an idea of how much force is in those tendons, you have 12 strand tendons and with 270 KSI steel. I mean, a normal rebar is A36, so 36,000 PSI tensile strength. These strands are 270,000 PSI, and we're stretching those about 3 feet. that's how much force we're putting in that. So we're actually taking that tendon with that jack, and it's like a huge rubber band, steel rubber band, that's tightening that concrete back up and closing those cracks. So it's not as simple as that, but I mean, that was kind of the gist of it, was to reinforce those shear zones and those anchorage points and recompress the bridge essentially.
Okay, very good. Here's another question. How does the owner decide when to implement some more significant, structural monitoring type of operations? What typically triggers that kind of a decision? Because it's certainly not an easy decision to come by. There's particularly, usually a pretty good cost and time associated with that.
Yeah, I mean, whenever you see cracks that are moving or propagating in a short period of time, even between inspection cycles, that makes everybody a little bit nervous, right? I mean, if you build a bridge and you get a shear crack happen after the year it's open, and it just stays in that condition for the next cycle, the next few cycles, and you're not getting more cracks, or those cracks aren't growing or getting wider, you usually don't get too nervous about it. You just kind of keep an eye on it. If you're going out every inspection cycle or in between inspection cycles, and you're like seeing 3 or 4 more new cracks, or the cracks are getting wider, or you're seeing anything move under traffic, to me, that's going to trigger structural health monitoring, or getting another group of experts out to do a deeper dive into why that's happening. So I would say crack propagation is going to trigger me to do structural health monitoring 24/7, so I can keep an eye on that thing.
Okay.
And it would be shear cracking, flexural cracking, tensile cracking, your main, tensile cracking in your max moment areas, shear cracking over your bearing locations, and then any kind of crack growth, propagation in those spots is going to make me nervous and want to monitor it in real time.
Okay, yeah, that makes sense. All right, couple of additional questions. So you mentioned overlays, and overlays are, I think, considered as a separate bridge management element when you're doing your ratings. Mm-hmm. A lot of segmental box girders feature what's called an integral overlay, which is essentially, in its simplest form, just additional cover concrete at the top surface of the deck. The advantage being, of course, that it's pre-compressed along with the rest of the cross section as it was being constructed. How do you guys handle a bridge with an integral overlay? Is it considered a separate bridge management element, like a secondary overlay, or do you do it in some other way?
I would still probably identify it as a wearing surface, just because, I mean, it could be maintained, it could be removed and replaced if you had to. I mean, obviously you would lose a compressant at that point, but it's still sacrificial in terms of the structure itself, and just to monitor in that condition, because a lot of your deck or your top flange condition rating is going to be driven by what you see inside the box from the underside. So you want to keep them separate so you can maintain them effectively. I mean, if your wearing surface, or that concrete, because it's non-reinforced in the top there a lot of times, is cracking up and failing or needs some patching, that's a lot easier to maintain than if you're dinging the entire deck rating based off the condition of that wearing surface. So you don't want to set up, I guess, false alarms and think you're having major issues with your top flange or your bridge deck, when it's just your wearing surface that maybe had a bad cure on it or something, or it's starting to break apart to get some D-lams.
Okay. All right, and then one more question here. Are minor cracks that might be located inside the box girder, sort of out of the weather, are those considered to be less of a concern than minor cracks that might be, of a similar nature, that might be located on the outside of the box girder and therefore, more exposed to the weather?
Yeah, I mean, inside, I mean, I know Zilwaukee, we've got looks, you know, like a rainbow in there with the color-coded keels, you know, in between detailed inspections, because that bridge in Michigan was getting a detailed inspection every 4 years. So it was the quick routine every 2, and then a real thorough detailed every 4. But yeah, you're right. We would document those cracks, but we didn't jump to doing a crack sealing operation on those right away. Where on the ones on the outside, they're absolutely right. We would try to seal those up the best that we can because they are susceptible to the weather and you know, moisture infiltration. Another thing on Zilwaukee, you know, in the northern climate is we didn't allow chloride salt on that bridge. So there was another de-icing agent that we used, particular just for that bridge, and then a mile either side of it, we weren't allowed to use salt for winter operations. And I think that's gone a long ways towards keeping that bridge in the shape that it is, and not having a bunch of rusting steel deterioration as part of that.
Yeah, what's the material that Michigan DOT uses out there for de-icing?
Yeah, it wasn't. I mean, I want to say it was like, was it a calcium chloride? I can't remember what it was. It was a non-salt de-icing alternative, and I know beet juice was one of them too, which I know they use that down south too. It's kind of like a pre-treatment. So if there was a winter storm coming, they would get out and pre-treat with like a beet juice, organic, and then they had I can't remember what the name of the other product was that they put out for de-icing, but it was a non-salt product that they had at the maintenance facility.
Okay, great. Well, that wraps up all of the questions from the audience. So, Greg, I'll turn it back over to you.
All right. Well, thank you, Wade, and thank you, Corey. Appreciate your presentation today and your remarks, and particularly appreciate your emphasis about joints. You know, because for segmental bridges, that is a remarkably important detail, because you have pourbacks that are that are susceptible to corrosion, and water inside of a box is always a bad thing. It's always one of the things to look for, is make sure you're crawling inside the boxes and looking for. We've had boxes that had standing water for, you know, who knows how long, and you know, that's usually a pretty easy fix. So again, so thank you, Corey. Appreciate your presentation. Great job today. And again, everybody, our next webinar will be in February. A lot of folks always ask the question about when's is the presentation going to be available, and the answer is yes. We'll get a copy from Corey, make a PDF. You'll find it on the website along with all of our previous presentations. We'll have a PDF of the slides, and then also a link to the recording, and you can look for that probably later this week. So with that, we will log out and call a close to today. Appreciate everybody joining us, and enjoy the rest of your day.
Thanks, Greg. Thanks, Wade.